Friday, weekend, and morning. So that's why not so many students come. Okay, it's okay. Okay, so let's quickly review what we have learned. Let me check whether I have recorded or not. Okay. Okay, let's quick review what we have already learned last week. Okay, so this is week 1. So we have definitions of ceramics and ceramic structures, traditional, advanced, and also we spent a pretty long time explaining these crystal structures of ceramics and the characteristics. Okay, so maybe I use a bit of my pointer here. So for the objective, so we need to understand the chemical bonds in ceramics, okay, and the concept of a crystal structures in ceramics, and also the minimal cut. As I said, this is VIP, okay. So it's good. You should, I mean, you have to understand this one very clearly, okay. And also understand the crystal structure of some typical ceramics and the characteristic. Okay, so this one is not required. Okay, no worry. So the summary. Ceramic AB. So A is metal or non-metal. B have to be non-metal, which means no matter what, you have to have non-metal somewhere. Okay, this make you have a ceramic. And structure. So structure, we said we have 4 different levels. We start from subatomic. Subatomic for this one is multi-ionic and can be partially covalent. Okay, because this covalent later you can see is going to influence the crystal structures. And then atomic, we have crystalline and amorphous. Okay, so in the crystalline, you have 7 different crystal systems. Okay, and the nano, we have 0, 1, 2, 3, 1, 2, 3, 0, 1, 2, 3 dimensional structures. The macron, okay, so in your FYP, many of you are going to deal with this level more. Okay, so this also some of you may have. Okay, but this is more. So microstructures, so you have to know the grain size, the shape, the distribution, grain boundary, blah, blah, blah. Okay, all these details you have to provide the information to your supervisor and also the examiner write in your report. And advanced and traditional. So what are the advanced and what are the traditional? So actually the basic thing is the magnitude finer and more uniform. Okay, so the structure is much, much, much better controlled. Okay, and what is structural functional? Okay, the structural is anything deal with mechanical. So this one is anything deal with mechanical, and the rest is functional. Okay, and also in this section 2, we talk about the factors affecting the structures. So crystal stoichiometries, radius ratio, we said these are the 3 things, okay? So determine the crystal structures, okay? The first one is very simple, you learn in your high school, okay? So these 2 are the more recent ones, okay? So we have known that the crystal structure, number 1, you have to have the charge balance, right? As I said, so this is a very simple one. And also, this is the new thing here, the RC over RA. RC over RA, okay? So RC over RA is going to determine your coordination number, okay? So you are going to, and also there's a special thing here, which is ionic bond. So which means the RC over RA determines the CN is only if your bond is very ionic, okay? Once you have a little bit more covalent, so that table, the RC over RA, you cannot use anymore. Okay, and also we have learned like rock salt. This is rock salt structures, rock salt. Okay, then we have cesium chloride, this one. Okay, and also we have zinc blende. So zinc blende is a unique one. So zinc blende is basically this one. Okay, so 2 and 3 is just following this RC over RA table because it is very ionic. But zinc blende, because there's more covalent bond inside, so they have something special. Because it's supposed to be from the RC over RA is supposed to be 6, okay? But okay, in the end, I only have 4, CN4, it's not CN6, okay? So this is the zinc blende. And also for perovskite, okay, so AbO3, so we have corners. So corner items only considered as 1 out of 8. So edge, so this one don't have edge by edge, which is 1 out of 4. Phase is just like oxygen here. Phase is considered as 1 of 2. Body is in the center. Okay. So today we're going to talk about process. So you can see this whole course, right? I have designed in such a way. So the week 1, we talk a lot about the structures. Okay. Then the week 2 and 3, we talk a lot about the process. So how do we make ceramics? And week 4 and 5, we talk a lot about properties. Okay, so if you see clearly what we have seen, okay, so week 1 is structures, all sorts of structures. We said like nanostructures, microstructures, crystal structures, all these are structures, okay? So then this week we have process, okay? And also the week after, weeks 4 and 5 is about properties. So as I told all of you, as a material scientist, you always need to find the relationship between these 3 things. Okay, so this one we call the interrelationship between the property, the process, and the structures. Okay, so these are the big 3 things of material science. So that's why the course is arranged in this way. Okay, so we move to the process of ceramics. Okay, so we will have the powder synthesis, and the essence of this course, we're going to spend a lot of time to explain this sintering, because compared with metal and polymer, ceramic need very high temperature, which is sintering. Okay, so that's a very unique thing of ceramics. Okay, this is the VIP, okay, of this part. Okay, so let's continue. So the basic learning object, let's understand the basic root of process of ceramics. Okay, so this one you can simply just remember as a bake a cake. So later I'm going to share with you how can we bake a cake. Okay, then we talk about the steps in solid state reactions, understand what is liquid and solid state reactions, solid state centerings, and what is occurring during centering. Okay, so these 2 are the fundamentals. In the end, actually, in all material science, in the end, it's all about how atoms move. So atoms move from where to where. Okay, so these are the fundamentals, and we're going to let you know in centering what happens for these particles and vacancies, how they move during the centerings. Okay, so then we're going to explain 5 atomic mechanisms during the centering. So this one again is talk about how atom moves during centerings. Okay, use what we have learned here. Okay, so once we know, so this part are the fundamentals. It's very heavy math there, so please be patient with me. Okay, so at the very beginning, all of you will feel very decent. Don't worry. Okay, based on my previous year's experience, students found at the very beginning too many math manipulations, too many fundamentals. Okay, but after the class and also after the tutorial, 95% students will understand. So no worry. Okay, so just be patient with me. Okay. Okay, then we will know that understand the factors determine the sintering products and describe various mechanisms in the liquid. We said, okay, so we have so many things about solid. So why liquid stand out in terms of certain things? Okay, and also the last one is always structure and properties. Okay, so this interrelationship you can never escape as a material scientist. Okay. Okay, so now we move to the universal way of thermodynamic stable compounds. So how can we produce a ceramic? So this is a very universal way. Okay, so basically remember, just use an analogy of baking a cake. So what you do, you crush and mix the starting powders. So it's just like you mix flour. Okay, so then you press to get a certain shape. Okay, so this you get a shape. Just like make a cake, then you get a cake, right? You get a starry, then you put a shape. Press in order to achieve large contact area. Then you press it because you need to press these powders and make it come together. Later, it's easier for you to sinter, to bake. Okay, then heat the mixture so that species diffuse and reactions to desired products. So that's the stage which is sintering. So sintering. So this is the essence of this course, of these 2 weeks. Okay, so the sintering occurs. Then of course you need a little bit post-treatment, right? So that's the post-treatment. So as I said, use bake a cake to remember. Okay, just in case you haven't done any experimental things before. Okay, so okay, so these are the basic rules. You have the ceramic powders with some sintering additives such as binders, lubricants. Okay, remember as like you put a flour and egg. Okay, then you mix. Normally we use a ball milling, is the most common one. So some of you, if you do your FYP with ceramics, so most likely you will use a ball milling to mix. Okay, mix ceramic powders and the sinterings. Okay, then sieve, just break down the agglomerations, just sieve. Okay, then you form a shape. So there's a name here. So this one still requires a green parts. Green parts. Okay, so green parts, which means you haven't baked yet. It's just like a green papaya. Okay, it haven't ripened yet, haven't baked yet. Okay, green parts. Then the essence is sintering. So you need to put inside the oven and heat up at high temperature and fry it and make it solidified. Okay. And the last one is machining and polishing. So this is a flow chart for the ceramic sinterings. Okay. And I show you a video and quickly just what's happening in this. Can you see the screen? Give me some, please. You can, right? I guess. Okay, so this one is okay. Thank you, Jay. Thank you. This is ceramic powder. The additives, and these are the grinding media. Okay, this one. Use it to crush ceramic down. Okay, see, after ball milling, you sieve it. Okay, so this is the finally ball milled one. Okay, so you can see, right, is it like a bake a cake? Then you get a shape, then you set in the oven and get whatever. Okay, okay, it looks very simple, right? Okay, a lot of mass behind. Okay. So let's continue. Okay, so we very quickly talk about this powder synthesis. Okay, because you see, sintering, you always start with powder first. So we have to know how can we produce good powders, because in the end, you will know it's going to influence the microstructure of the sintered products. Okay. So these are factors of the particle influence the final product, such as a particle size distribution. Okay, particle packing, the void fraction and distribution, and volatile content. So all this is going to influence the end product. And these are important powders. So for example, like oxide, alumina, zinc oxide, ether, and titanium, and nitride, carbide, boride, and others. Okay, and the synthesis have a large influence on the final product of the ceramics, such as we have so many ways you can produce these powders. Okay, for example, like soil gel, carbon thermal reaction, so many. Okay, but in this course, we only talk about the solid state reaction. Okay, solid state reaction. So in particular, we're going to use ball milling to have these solid state reactions. Okay. So this powder synthesis ball milling is based on kinetics. So you've already seen, right? So you just put inside the jar, and also the powder is inside, and use a grinding media, then either roll or hammer falling or canister revolving, whatever, give them some like a mechanical kinetic energy and to crush it down, to mill it down. Okay, so the ball milling is a mechanical attrition. So the rotation or rapid vibration of the canisters in the grinding media. So just now you're already saying, I think that one is a tungsten carbide ball bearing. The beads, we have seen like the big beads. That bead is requires a grinding media, okay. So stainless steel actually is not very often used. Okay, the tungsten carbide ball bearing is more often used. Okay, so the purpose for ball milling is to reduce the size of the coarse-grained particles, okay, because your starting particles may be too big or too ununiform. So then we can use this ball milling to reduce the defects, okay? And also because at the very beginning, maybe the particle size, they have large variations, maybe some like 100 microns, some maybe like 1 microns. So you need a crush done to make it maybe everything is about 1 micron to 10 microns, something like this, okay? So these are the purpose of the ball milling. And in the ball milling, so what happened in the ball milling? Okay, so basically they have compact the arrange of the particles, okay, then followed by the elastic and plastic formations. You even may have welding. Okay, and the welding is actually not wanted because you can imagine the large particles, right? You want to actually break it up. Am I correct, right? To make it smaller, crush to make it smaller. But sometimes because inside the temperature is so high, so might even weld them. So all sorts of things can happen. So it's not easy, okay? So the most important thing is once you do so, you will have these particle fractures and fragmentations. Fragmentations means the particle is going to become smaller and smaller and smaller. Okay, and also the crushing, the strings are the crushing strings. So the stress related with the quark propagation, because you need to make the quark, right? Large particles, you need quark through, okay? It's going to actually, you can say, is inversely proportional to the quark size. Inversely proportional to the quark size. These are the constant. Okay, which means what? Okay, this is a very important concept here, which means when your particle become smaller and smaller and smaller, the stress you need is going to be higher and higher. Okay, so this is inversely proportional to it. Okay, so which means what? Which means the particle becomes smaller and smaller. It will be easier or more difficult? More difficult, right? It will be more and more difficult to make it become smaller because the stress needed is going to be higher. Sorry, it's higher and higher. Okay, so this one just show you it's not easy to get very small particles. Okay, so the rationale or the science behind it is this, we call it Griffiths theory, and these equations we're going to learn a lot in week 4 and 5. Okay. So continue. I give you one example here. Okay, so this is also good examples for you because you're year 3 already, right? So next year you're going to be year 4. So I just give you this as an example to share with you what is supposed to be a full and good FYP report. Okay, so we can see. So this is a ball milling examples. Okay, so you need pay with the stress and maximum energy as we just already saying, right? Use this Griffiths equations. We know it's going to be more difficult, okay? And also we know it's going to be higher and higher resistance to fractures because once your particle become too small, so the stress needed to make even smaller will be higher and higher. And also once the particle become too small, it's very easy for them to agglomerate together. Not only weld is very bad already, but they can even agglomerate together, which means they're too small. So the surface tension is quite high, so they're going to agglomerate together. Okay, so I give you these examples. For example, so you have a copper and iron. Okay, so these two metals powders, you ball mill them together, okay? Then what they use a tungsten carbide, which is a big grinding media. So use this tungsten carbide, and in the end, you will get a nano-sized powders. Then you follow by the heat and pressure. So this one is a heating, this one is more or less like sintering, right? So this one is like a ball milling. Okay, ball milling. Okay, so in the end, by doing so, this ball milling, you can reduce the particle size to 40 nanometer. The average grain particle size is going to be only 40 nanometer. Okay, in this range, which is 15 to 75 nanometers. But the pure apple, which means the pure iron at the very beginning, when you put inside the ball milling, it is actually 50 nanometer to 100 micron. So you can say it's a very large variation of the particle size. That is very often. Okay, so you intrinsically will know, right? If you want anything uniform or very much controlled, so your starting powders have to be very uniform and well controlled. Am I correct? Okay, so you start with something like iron has very, very large particle size, okay, and very large variations of particle size. Not only particle size like 150 micron is huge, but also there's a very large size distribution form 50 nanometer, which means it's very ununiform, 50 nanometer to 150 microns. But after the ball milling, so you can see, so this whole thing become much more uniform. Then the good thing is what? The good thing is after all you done all this process, right, you will get a fracture stress, which will be higher, 5 times higher than just the pure one. Okay, so this is a very good example to share with you. So this is about process. Am I correct? You use ball milling, you reduce down the size, then you follow by the sintering. Okay, so this is a process. So which part is the structure? So we said before, right, process. Okay, process. Big three science are ceramic hours, material science are process. So process, what you process you design is you use a ball milling, then you get a very small size, then you put a heat to apply and pressure to get your densified bulk materials. Okay, and the structures is, okay, the structure is, okay, this is structures. So the average grain size now is only 40 nanometer. 40 nanometer. Okay, so that's very, very impressive. Okay, so structures and the properties, what? So property is this one. Our property is the fracture stress is 5 times higher than the pure iron. Okay, so this is property. Okay, so this is a design of your whole of just one project. So as a FYP, you need design your project in this way. You need change the process. Then you go and use SEM or AFM or whatever machines to let you know what is the structure inside. In this case, the structure, which is the grain size, reduced to 40 nanometers. And the properties, then you measure the properties much better than you before without doing anything. Okay, so this is a very good examples to share with you how you can go, how you can design your project in such a systematic way. Okay. So let's continue. Okay, process, structures, and properties. Okay, so then I'm going to give you examples now. So it's not difficult, right? It's not difficult. I just like you always remember bake a cake, then you will know what I'm talking. Okay, for example, now we are talking about one classical solid state reactions, what they do. So what they do, they need produce this magnesium. Sorry, where's my mouse? Okay, it's here. Magnesium aluminum oxide. Complicated, looks like AB204. Okay, look very complicated, but how you produce it is not that difficult. You simply use magnesium and aluminum, then ball milling them. Okay, so this is one of the very classical solid state reactions. So solid state reactions, which means what? Which means you cannot, the sintering temperature cannot be higher than the melting temperature. So which means everything still happens at the solid state. Because once if you heat up to melting temperature, it becomes liquid already, right? So nothing is ongoing in the liquid phase, okay? It's still in a solid phase. Okay, so because this happens below the melting temperature. Okay, that's solid state reactions. Okay, so let's say the one examples. So you ball milling the aluminum and the magnesium. Okay, so you ball milling them, then you sinter at very high temperature. So you're going to form this seed. So this seed in the interface between the magnesium and aluminum. So this little bit seed of the crystal here, it is already magnesium, aluminum oxide already. Okay, so this one, you ball milling them, then once you mix very well of the magnesium and aluminum, so they will form an interface. If heat up at high temperature, you're going to form this magnesium or aluminum oxide. Okay, okay, so then the seed become bigger and bigger and bigger. So that's what we hear, the growth of the seed. So now the whole area here is going to be magnesium, aluminum, 2, oxygen 4. Okay, so not that difficult, right? So possible product, you could form like a small crystals, powders, and even single crystals if you control very, very well. Okay, of course it's not easy. Single crystal is super difficult. Okay, so this is one example. So I'll give you another example. So this etcher barrier copper oxide. I think your your how to say, your batch, some of you may still go to my MS 8301 before, right? The material and the map. Actually, I talked about this material before, if you still remember. So this is a very famous high temperature superconducting materials. Okay, you can just search by yourself. Okay, so yeah, let me see, some students said, yeah, correct. Yeah, Yongjing, it is a superconductor. It is a high temperature superconducting materials, high temperature. Okay, so if you want to know a little bit more, please Google from the website, and just give you some words here. So these materials, this type of materials won Nobel Prize in 1987. Okay, so for their important breakthrough in the discovery of superconductivity in ceramic materials. Okay, so which means at very, very low temperature, the ceramic is not insulating anymore. It is superconductivity, which means the resistance is going to equals to 0. Okay, so this is a breakthrough in physics. Okay, and also, okay, just we talk about Nobel Prize. Okay, and also there's another Nobel Prize, which is this good enough. So this one is also a ceramic. So it's a lithium cobalt oxide. Lithium cobalt oxide. Okay, so this is a lithium and battery materials. Okay, and also it's a ceramic, and it's won a Nobel Prize. Okay, these are good enough. This person is 90 some years, 90. I think it's 100 years this year, because this Nobel Prize is 2 years ago already. So this year he's 100. Okay, because the Nobel Prize can only give to the living person. Okay, so it's good to enjoy long life, right? I'm just joking. Okay, go back. go back. Just some like stories here. Yiche barrier copper oxide, difficult, right? Looks very difficult, right? Yiche 1, barrier 2, copper 3, oxygen 7 something. Okay, very complicated. Looks very complicated. But you can also use this very primitive, like a ball milling way to make it. So we can use just add a bit barium oxide, copper oxide, yiche oxide. You put these 3 things together, you ball milling. Okay, mix them very well. Then you heat up to like 1000 degree here, roughly. Okay, so you heat up here. So at this stage, okay, so the powder mixture is pressed into a dense pellet and heat up at 930 degree. Okay, so in this case, you form yiche 1, barrier 2, copper 3, oxygen 6.5. Not bad already, right? You see, if not, let's say I check the property, I found the property is not nice. Okay, so maybe I want to increase this oxygen, not 6.5, like 6.7, 6.8. So how you can do? Can you type your think here in your chat box? How can you do? Because 6.5 not good enough. Yeah, Jay. Yeah, Shan. Thank you, Jay and Shang. Or yeah, correct. So you have some basic concept of ceramic already. Very good. What you can do? So Jay and Shang answer correctly. Okay. So what you can do? You annealing them. You anneal them at 500 in oxygen, not just oxygen. Increase a little bit. 6.5 is not good enough. I want 6.9. So increase to 6.9. Okay. So you see, not that difficult, right? All these are Nobel Prize winning materials, but you can do it in your FYP research lab. Okay, and then you cool down. Okay, so this is yiche barium copper oxide, right? It's not difficult. Okay, so of course you can use other precursors like barium carbonate, okay, nitrate, oxalate, like all these other precursors. And of course, be careful with your containers. Make sure you won't react with the containers. This is more or less like a common sense. Okay. So continue. Okay, so in this tutorial, starting next week, so actually I have two questions talking about how, since we already know like a strontium barium titanium oxide, you know how to make it already, right? But in the end, if you go to the lab, you still need to calculate. So how much you need to put in strontium oxide, barium oxide, titanium oxide. So how much exactly you need to put in. So this one actually you have learned before in your high school chemistry, but we are going to give you 2 questions to understand it. Okay, just more or less like review what you learned before. Okay, so because this is the first step if you go to the lab. for example, your supervisor asks you to produce this ceramics. So the first thing you need to do is you need to weigh, use a balance to weigh, okay, how much gram of this strontium, barium, and titanium, all the things you need to put inside the ball milling machine, okay? So this one we're going to explain in the tutorials because more or less now you have learned before. Well, annealing be the only process to increase oxygen composition so far, yes, if it's sintering case. Sintering is the easiest one for just put a little bit more oxygen inside. Okay, so let's quickly review what we learned so far. Okay, so the basic rules is ball milling, sieving, shape forming, and sintering. Okay, ball milling, sieving, shape forming. I will always use a big cake, baker cake. Okay, ball milling, sieving, shape forming, and sintering. And ball milling, what is ball milling? So ball milling is rotation raw powders in a grinding medias. Okay, you see, it looks like simple, right? But actually, the ball milling, if you do very well, like even 10 years ago, some people can even simply just use ball milling to get a PhD. There's a lot of things you can play with. Okay, so ball milling, the purpose of ball milling is to reduce the size of the coarse particles. Okay, and the classical solid state reaction is A plus B equals to AB. Okay, you ball milling them, you heat up at high temperature. So this is a very classical solid state reactions. You can do it in your research lab for your FYP. Okay, to make very complicated ceramics. And also you can do a bit post-treatment to tune the stoichiometries. Okay, students have questions? Okay, thank you. Okay, so we move to a difficult part, sintering. As I said, please be patient with me. There's a lot of math here. Okay, so I will guide you. And even you don't understand today, no worry. After 2 tutorials, you will understand it fully. I'm very sure that's based on my experience. 95% of students will understand the concept very, very, very well. Okay, no worry. Okay, so now we move to sintering. So it's the difficult one. Okay, so what is sintering? What is sintering? Okay. Can we sinter without sieving? Yeah, of course. But sieving, it helps because can just reduce the size distribution. You want to get more uniform size, then your sieving can help. Okay. So sintering is processed by which a powder compact is transformed to a strong, dense ceramic body in heating. Okay, keywords is heat up. So if you compare with metal and polymer and the molten cast machine and forge into final shape, it just happened I am also teaching this portion for year 2 at the same time. So I have 2 courses. So if you have anything to consult me, please every time write, I'm from MS 3011, okay, because I have 2 courses running at the same time. I also teach this metal, machine, casting, and forge, okay, at the same time, okay. And ceramic is very different, okay. So the ultimate goal of ceramic is how to consistently obtain ceramic density at the lowest possible temperatures. Okay, so it is very difficult. Why? It's because the driving force for sintering is just a few joule per mole. But any chemical one, okay, it is actually K. Okay, so you can see, so it's 1,000 times higher. So driving force is much, much higher. Okay, so it is difficult, but it's useful and it's effective, right? You have already seen that you can even use a very simple ball milling and sintering. You can get Nobel Prize winning ceramics. Okay, so let's start it. Okay, so the ultimate goal is how to consistently obtain ceramic density, which means the density, the higher the better. The 100% is the best, but temperature cannot be too high. So lowest possible temperatures. So you can see this one. So this is the some materials. Okay, so like this is time which you sinter longer time. So this temperature T1 and the T2, which means you sinter the same thing at 2 different temperatures, T2 and T1. Okay, so this is delta L. So delta L means what? For example, if let's say if I sinter something like a bar here. Okay, at the very beginning is something like this, right? Okay, at the very beginning, maybe the length is 10 centimeter. Okay, but after sintering, it is 8. Okay, 8 centimeter. So the change delta L is simply just is 8 minus 10 divided by 10, right? That's a delta L. Okay, so obviously this one is higher which means you're more densified. So let's say if only 6, which means you're more densified. Okay, so obviously delta L is to show that whether you're more densified or less densified. So in this case, you will see that T2 is larger than T1. T2 is larger than T1. Okay, so from here, you know which one have higher density, T2 or T1? T2 or T1, which have higher density? Yongjin, Hongyu, Shang, Jay, everyone can type. So T2 and T1. So which one have higher density? So the one you have more shrinkage, right? More shrinkage, which means you're more densified. Okay. Yes, T2, correct. Thank you. So T2 have higher density. Okay. So that's what we put here. So in general case, which is higher temperature sintering is going to give you higher density. But obviously, economically, you cannot afford too high temperatures. So that's why we put it here, how to consistently obtain higher density. Theoretic one, which means 100. You have no pores inside. Everything is your materials, is your ceramics. You don't have any pores inside because you have more pores, you have less density. Am I correct, right? So density and porosity is opposite, okay? So density equals to 1 minus porosity. Less pores means you're more densified. Okay, so we know that higher temperature, you're going to have higher density. So the ultimate goal is how can we make this one more densified at lower temperature. So there's all sorts of skills and tricks we can learn later. Okay, so let's continue. Okay, this is ultimate goal. Okay, so then we have 2 types in terms of how we sinter them. So this one is very often the solid phase sintering, which means now you start with solid, in the end you have solid. Okay, but this unique thing, the liquid phase sintering is a little bit special here. So which means you have A here, just like this is A, so everything is A. Okay, so in this case you have A here, A here. Okay, if you don't put anything, so it will be something like a solid state sintering, right? But if let's say I put some B here, which means another materials. So this B have a lower melting temperature. So if I heat up, okay? So this heating up temperature is still less than the melting temperature of A, but B is already melted. Okay, so the thing is, once the B melted, so it become a liquid in between. So this is liquid in between. Okay, so this one requires a liquid phase sintering. Liquid phase sintering is very good. It's very good. It's going to help you to achieve this goal. Okay, to have higher density with lower temperature. And why? Okay, I give you the keywords here first. So we're going to learn this next week, which is once you have a liquid in between, you're going to have very high capillarity force. Okay, you can write down first. So later we are going to explain the details. Okay, no worry. Okay, so there's 2 types, liquid phase sintering and solid phase sintering. Okay, so let's continue. Okay, so for densification to occur, so you have to make sure this one, this is a condition. This is a condition. Okay, so gamma GB and gamma SV. So how does this gamma GB and gamma SV? Okay, so basically you can imagine why. Okay, so I give you an answer here. Okay, so for example, so this one you have 2 particles, right? 2 particles are both particle is solid, right? Correct? Both particles are solid. Okay, so which means now, so this particle, so the surrounding is what? Surrounding is what phase? Tell me. Is liquid phase or vapor phase or gas phase? Surroundings. So this is solid phase. Vapor, your copper, vapor, okay, vapor phase, okay, correct, right? Outside is vapor phase, right? Vapor phase, which means now the vapor and the solid, they're going to have a surface tension here. So this is gamma, okay? So gamma SV, because it's happening between a solid and vapor, okay? So that's what we put here. You have gamma SV, correct? Correct, okay, so gamma SV. Now you come together. You still have these 2 like solid particles that come together. They're going to form something like this. For example, this one is still solid, this one is still solid. So now I'm asking you, what is this force change? This gamma change to, is still SV? Is still SV? So what is now the surrounding of this? What is the interface of this solid now? It is actually it's solid already, right? Correct, because this side is solid 1, this side is solid 2. So actually you have to change to SS, but we have a name for this one. We change it to grain boundaries, because when they come together, they will form a grain boundaries. That's why we put a gamma GB. Gamma GB is actually just gamma SS, because now you have S here, S here. Okay. Yeah. Okay. Okay. Good. Okay. So then now, why densification happens? So this one have to fulfill this whole thing. Okay. So the basic concept is you need to have a mechanical equilibrium, right? Because now you see at this interface, you still have, because this is outside is vapor, so you still have a little bit gamma SV, okay? But then these three forces need to get this balanced, mechanical balanced, okay? So that's why the gamma GB is going to equals to 2 gamma SV, do a little bit like this. Okay, 2 gamma SV cosine, this angle you have to half, right? Half them. Okay, so this is the equation to achieve this requires a mechanical equilibrium here. Okay, so obviously, so this whole thing is going to be less than 1, correct, right? Cosine, anything have to be less or equal than 1. Most we just simply say it's less than 1. Okay, so then the gamma GB is actually should be less than, okay, gamma GB is actually less than 2 gamma SV. Because cosine, this cosine is going to be less than 1. Okay, so that is for densification. This is one of the conditions. So let's move on. Okay, so for example, so now let's calculate 1 mole of oxide, the enthalpy change of 0.5 micron spheres, which are centered as cube, given that the dihedral angle was measured to be 100 degree. The surface energy is 1 J per square meter, and the molar volume is 10 centimeter per molar volume. Okay, so please calculate everything in 1 mole, so it will be easier. Okay, so 1 mole, then how many numbers of particles by yourself? So whether you start with particles, so whether you're going to center together later as a bulk materials, whether this is going to happen or not happen, only determined by one thing, which is the total surface energy. Okay, so this is thermodynamic. This is general rule, universal rule. This is a rule. Okay, so you have to make sure you start from powders. So when you center together, you have to calculate whether all this total energy is going to get reduced or not. Only if it's get reduced, you're going to have this direct reaction to happen. Okay, so now let's see whether this whole thing is going to happen or not. Okay. So let's do this calculations together. It's a very simple calculations. So please follow me. Okay. So let's see. So you start with particles, right? Solid particles. Okay. In the end, you will get a cube. Okay. So here you have 27 particles, right? Here you have 27 cube, right? Correct. Just 1 to 1, which means in the end, my 1 sphere change into 1 cube. Okay. This is a simple thing here. Okay, so let's calculate, follow me. Okay, so first of all, let's calculate what is the total surface energy of this system. So total surface energy equals to what? You should have learned in many courses already. Tell me. So what is the surface tension here? Gamma what? Gamma what? Can you write down gamma? This is S. The outside is what? Outside is vapor, right? Gamma SV, correct? Gamma SV. Okay, so you know that for each of these particles, you're actually, because you're not contacting with each other, you're only contacted with the vapor. So for each of particles, you have gamma SV, right? So how can we get the total energy? You just times what? So for each of them, what is the surface energy? Gamma SV times what? Gamma SV times surface area. gamma SV times surface area. Okay, so the total energy, okay, total energy, okay, is equals to gamma times the surface area. Okay, so what is surface area of this one, of these particles? What is surface area of this one? It's just 4 pi r, right? 4 pi r square r, okay? But now I have so many. If, for example, I know in 1 mole, I have how many numbers of these particles. Then you simply just times, you know, for one already, the energy for one, so the surface energy for one, then you just need times how many of them, correct? You will get in 1 mole, what is the total surface energy, correct? Right, it's not difficult, right? It's just simple math, right? Okay, okay. Now let's start. Okay, the total surface energy for this case, this is starting case. We start from what? We start from particles, loose particles. This particle is in contacting with the vapor, okay, so that's why actually this one gamma is what? You just already wrote in the chat box, it's gamma SV, gamma SV. So the total energy is going to be equals to area, which means area is one sphere, okay? One sphere, okay, times gamma SV, then times number, because we know we need to know in how in 1 mole how many numbers is going to be these particles. Okay, so you have so many particles, just you times 2, times 3, times 4, times n. Okay, so let's continue. So first of all, how can we calculate n? How we know in 1 mole? How many numbers particle there? Because in this question, I have already given you in 1 mole, what is the volume already, right? The molar volume is this. Molar volume is this. Okay, which means now in 1 mole, the total volume is 10, okay, centimeter cube. Okay, then how can we calculate the numbers? It's also an approximation, because you know in 1 mole, you're going to have this number of volumes. This is 1 mole volume, okay? You simply just need to divide it by the volume of each one. Again, it's approximation, okay? Each one. Then you will know the numbers of the particles in 1 mole. Okay, can I move on? Can I move on? Yes or no? Or you can, it's easier because I found if you give me some, it's easier for me to say. Otherwise, I have to keep clicking the chat box. Okay, so this is a simple calculation. So which means now, okay, for example, I know in one, maybe like in a bottle. Okay, you know the bottle, the total volume of the bottle is V. Okay, so then inside you have so many particles. And you know each particle's volume. Of course, you may still have some space there, but we ignore it because that's not significant. Okay, each particles. So then people ask you how many particles inside. So the simplest way is you use the total volume divided by each volume of each particles, volume of each particles. Okay, so this one, this is number R. Okay, so then this one is a molar volume, which means for 1 mole of these particles, you're going to get this volume. Then you divide it by the volume of each particles. Each particle just volume of these spheres, right? 4 over 3 pi, this R cube, okay? R cube here, okay? So by using this one, the N is equals to, which means in 1 mole, you're going to have 1.5 times 10 power 14 number of the particles, okay? Should pi be in the denominator? 4 pi, okay. Anyway, this is, oh yeah, okay. Yeah, pi should be here, right? Sorry, thank you. Okay, hey, why so many yes? Nobody tell me. Okay, so yeah, pi should be here. Okay, it's not here. Sorry, I'm going to change in this, the notes, okay? This is volume of 1 sphere. Okay, this is numbers. Okay, so let's continue. Thank you. What's your name? Jay. Thank you. Okay, so let's continue. Okay, now it's easy already, right? Easier. So now we need to calculate in 1 mole what is the total surface energy here. The total surface energy is going to be equals to So first of all, for each of them, 4 pi r square, 4 pi r square. Okay, so this is area. This is for one sphere. Okay, so one sphere's area times gamma times the total number. You will get the total surface energy. Correct, right? So total energy will be area which is for each one. So this is area. This n, which is number in 1 mole. How many number of this particle times this gamma. The gamma always know as gamma SVR, because at this moment, the particle is not in contacting with each other yet. It is still in contacting with vapor, gamma SVR. Okay, so now this is 118. We calculate the after case. Now if I put them together, now it's become a cube already, Okay, so now this cube, so we also need to calculate the cube, the total surface energy. So now you can see between this each cube, right, we can ignore the surface because the surface, the contribution is very insignificant, okay, because it's too few, okay. So we only talk about the cube and cube in between. Okay, so now you tell me, what is this gamma now? What is this gamma now? Can you type? Between one cube, each cube, what is changed? Because before, right, this is gamma what? Gamma SV, right? But now it's in contacting with each other. This and this are in contacting now. So they're in contacting, which means they are not SV anymore. It's not this vapor, but the actually is solid and solid. So it's supposed to be gamma GB. Hong Yong, yeah, you're correct. Why every time you type a question mark there? You're correct. Be confident. Okay, confident. Thank you, Lida. Okay, yes. So because we said before you separate, you have two particles. You separate is gamma SV, but now you bond together. You bond together. Okay, so now which means you have solid and solid. So into solid, actually this solid is green boundaries. Correct. So first of all, we have to calculate what is the gamma GB here, right? So how can we calculate the gamma GB? Tell me. Yeah, we have this equation already, right? We already have this equation. We know this angle. We know gamma SV. Now we can calculate gamma GB. Gamma GB. We simply use the equation we just learned. Okay, gamma GB equals to 2 gamma SV cos 50 equals to 1.28 J per square meter. Okay, continue. We finish this one, then we can have a break. Okay, sorry to make you exhausted. Continue. Okay, so now, because as I said before, we assume just one sphere become one cube, right? As we said before, like 27 spheres become 27 cubes stacked together. Okay, now let's assume the length of the side of the cube, which is A. And always, there's very important assumptions in material. It's not assumptions, it's a general rule. You always need to have this mass conservation. No matter you have sphere, you have cube, right? So sphere and cube, you always have to have the same mass, and the density doesn't change. So in this case, which means you need to have a same what? Tell me. You need always have the same mass. You have the same density. So which means in the end, you have same what? Tell me. Volume. Excellent, Hong Yong and Mervicue. Yeah, your name's difficult. Okay, so, excuse me. Okay, so you need to have same volume. Okay, so then of course let's calculate this A first. A first. So A cube equals to 4/3 pi r cube. Okay, so then A is equals to 0.4 microns. Okay, now there's a tricky things here now. Okay, so you see, if my cube, right, if my cube is standard norm, okay, so what is surface area? Tell me, what is surface area? So the surface area, you have how many square for each cube? You're supposed to have what? 6, right? Correct. Thank you. You have 6, right? Okay. But the tricky thing here is what? Tricky thing is because it's standard norm, it's 6 thing. But now you're in contact with each other. So which means now if these two cubes come together, so this surface now, you actually have to be shared with your neighbors. Okay? This is a very important concept. Remember when we talked about perovskite last week, right? Perovskite, we said if you stay at the corner, you share with how many? You want atom share with how many? Now I'm testing you now. Leader? If the atoms stand at the corner, remember that one, right? 8. Excellent. Stand at the surface. Surface, how many? Like oxygen, that one in the purple sky. Surface. 2 lah. Okay. Okay, so same as this one. Now, if you cube, you stand alone, you're supposed to have 6. But now you stand together. You're in contacting with each other. Okay, which means now you change to, you have to divide it by 2, right? So now the surface area is not 6 surface anymore because you're in contacting with each other. So that's why we have to change to 3. 3. Okay. Okay, as I said, if you stand alone, the cube stand alone, you're supposed to have 6 pi. Oh, sorry, not pi. Sorry, yeah. Stand 6a square, right? Correct? 6a square, okay? But now you stand together because each surface have to share with the neighbors. With the neighbors, okay? So each of them have 1 neighbor. So then you have to divide it by 2. So that's why you can see you have only 3a square here. And of course you have how many? How many is still the same as previous one, right? Because you have changed from 1 sphere to 1 cube. 1 sphere to 1 cube. Correct? Okay, so in this case, now we know that the total area is going to be 72, the calculation. So what is the total surface energy? Now tell me, what is total surface energy? Simply you just use what times what? Gamma what? Use gamma. It is always use gamma times total area. Okay, but in this case, it's gamma what? Is gamma SV or gamma what? Yes, it is gamma GB. You have to change to gamma GB. So that's why the total energy after centering will be the gamma GB. Gamma GB times the total green boundary areas. Okay, then you're going to get 92J. So now can you compare? Before centering is how much? Can you go back to the previous one? Before centering is how much? 118. Thank you. The before centering is 118. Okay, before centering is 118. Okay. Now after centering, it is 92. So do you think this is going to happen? Yes or no? Can you type your answer here? Do you think this is going to happen? Because your starting energy is 118, but now after centering, the energy becomes 92. So do you think this is going to happen? Yes or no? Thank you, Ryan, Shaw, Yuzhen. Okay, thank you. Okay, thank you. Yes, that's what we, okay, remember here, I talked about this one before, right? So which is roughly this case, because now you have a surface. So this surface is actually in contacting, you have 2 neighbors to share, so you have to cut into 2, okay? So let's continue. So what is driving force? Now we are very confident to answer this question already. What is the driving force? What is the driving force? Tell me. Yeah, your total, you start with how many? You start with 118J, right? You start with 118J, but you end up with only 92J. So this is a difference. So this difference is a driving force for centering. Okay? Okay, okay, so that's what we put here. And also a tutorial, you're going to calculate another case, which is if I have small, again, I have small particles. So in the previous case, it's become cube stacked together, right? But now it's become bigger one. And also, could you please go back to calculate, use the same method, okay, to calculate. So whether this one is going to happen. So from small one become bigger one, is this going to happen? And yes or no? You simply just need to calculate again. This one you calculate already, right? It's 118, right? 118J. So go back to calculate this one. What's the J here? So then you tell me, is it going to happen? Yes or no? Okay. So this is the driving force for centering, which is to reduce the surface area. Actually, in a more, in a more precise way, we have to say is reduce the total surface energy. It's not about area. It's all about reduce surface energy. Okay, which is more scientific, precise. Let's have a break here. No worry, as I said, I'm guiding you through everything. Later, there will be more calculations, but be patient, okay? Stretch yourself, 1 hour already. Stretch yourself, exercise a little bit, and we come back at 10:40, 10 minutes later, okay? Thank you, I paused. Okay. Okay, so we learned so far about what is the driving force. So we have learned here from all these calculations, you can see the total energy after sintering is going to get reduced, right? So that's the essence. Anything, any chemical, whatever reactions, if it's reduced, which means it's going to happen. Continue. Okay, so let's continue. Okay, so this one you go back to calculate, then you let me know whether this is doable or not. Okay, so let's continue. So that's what we put here to reduce the total surface energy. Okay, so there are actually two different ways to competing. So what you have just calculated is more or less like this one. So you have loose particles, right? Let me use my pointer here. Okay, so loose particles now, loose particle is just like this is gamma SV, right? Gamma SV are standard known, so they have so many surface areas. So all these surface area are this, okay? Okay, but now you densify first. So as I said, the calculation we just assume as a cube. Cube is easier, right? But in most cases, it's actually something like this, okay? So you can see now this one changed to gamma GB. Okay, so this is one way you can reduce the total energy, okay, total surface energy, okay, so become densify first, densify first, okay, then following the later stage, we call it grain become bigger, the grain grows, grain become bigger and bigger and bigger. So this is one root, okay, so actually what you're going back to calculate is root 2. So actually I'm telling you the answer already, right? So obviously, if you go back to calculate, the energy definitely is going to be less than 118. Okay, it is going to be less than 1 way, but you let me know what exact value, okay? So the second case is it also can, the small particle first, but they don't become grain boundary. They become bigger and bigger. So this one we call it crystalline. So now I'm asking you, so if you want very densified structures, so you go to root 1 or root 2. Which root is going to give you more densified structures? Root 1 or root 2? Correct, right? Thank you. Okay, yes, correct. Okay, so it's root 1 is give you more densification. So which means now we have to make sure your design of your experiment to ensure the root 1 have the more if you want densification. Okay, so this is a very important. So that's what we put here. The pore gets smaller and disappear with time, and the compact shrink. Okay, but this case it become bigger and bigger. Then in the end, it will leave a lot of hole here to become a porous structures. Okay, so to understand what is occurring during the sintering, so all these things matter: shrinkage, grain size, pore size, time, temperature, initial particle size. To reach theoretic density, let's just suppress root 2. Okay, make sure you don't have too much crystalline. So this one, it is not wanted if you want very densified structures. Okay, so for example, you can see for this one, right, you can look at these graphs. So this is a percentage of theoretic densities become denser and denser and denser. Okay, so which means what this one is, so at the very beginning, the grain size does not really change much, right? Because it densified first, right? Remember from this figure? At the very beginning, the grain size does not really change, right? Okay, grain size, small, because densified. Only followed by the very late stage, the grain become bigger and bigger and bigger. Okay, so densification followed by the grain growth. Okay, and the crystalline also, this is crystalline. Okay, so the crystalline, okay, so the grain size keep become bigger and bigger and bigger and bigger and bigger. But the problem is this one does not help with your densification. It just simply become, the grain become bigger, but the pores inside does not really shrink much. Okay, so you can see these two extreme case. So this is root 2 and this is root 1. So root 1 give you densification, root 2 give you crystalline, but the real case is always this Y. You always can compete. That's why we said root 1 and root 2 are competing with each other. Okay, they're competing. So if you want densification, please make the root 1 win. Okay, if you want porous structures, make root 2 win. Okay, so that is the essence here. Okay, because starting from next week, we're going to understand by controlling some factors, we're going to make the root 1 happen more compared with the root 2. Okay, so this is what we're going to learn next week. Okay, so continue. Okay. And also there's another way. So for example, like if it's coarsening, which is root 2, right? So both the pore size and the grain size is going to increase at the same time. But if it's densification, your grain size does not really change at the very beginning. You only have your grain size become bigger later stage, which means make the grain become bigger later. Okay, so let's continue. So this is a very good example to share with you what is this grain growth. So at the very beginning, you can see the grain does not really grow, so become densified. So then with longer on the time, okay, because this is magnesium took the lumina sintered at the air as a function of time. So become bigger and bigger and bigger. So this is a grain size become bigger and bigger. And this is one grain, bigger and bigger. Okay, so this is real pictures. So I also give you a graph here. So for example, this is density. So the best is always if you reach here, right? This is relative density, which means the denser the better. And this is grain size. So you can see the grain size change. And if you want to have very high density, so make sure your grain does not really grow that much at the very beginning yet. Only start to grow at later stage. So by doing so, you will have higher density. Okay, so difference between these two is they put something like the dopants inside. So this one we are going to explain later. Okay, so this is help with the root 1 to help you to get densification, which means don't have the grain growth at the very beginning first. Okay, make the come together fast to become densified first and become grain growth later. Okay, so student ask questions. If root 2, the grain get larger, shouldn't densify decrease? Root 2 is just simply because, yeah, it's still the density is also going to increase a little bit, but it's just not as good as root 1. It is always comparatively. It's just even like this one, right? You still have an increase a little bit. Even this is root 2, right? So you have increased grain size, but at the same time, you increase a little bit of densities. The pores also become less, but just not as good as root 1. Okay, don't think these two things need to reduce at the same time. No, it is grain size also great, but the density also go up, but also become higher, also become more densified, but just not as good as the root 1 case. Root 1 is become very densified later. Okay, thank you. Okay. Okay, so I give you a real picture again. So this one is very densified, right? The L-centered iron oxide densified, right? But this one, if I put a little bit of this hydrogen chloride, so then it become very costly, right? A lot of pores inside. Okay, so obviously, so you can see this is a graph. This is time, iron oxide, and this is shrinkage. Shrinkage is always higher shrinkage, which means higher density, right? So you can see this is air, so the density is high. Okay, and you put a hydrogen chloride, so the density is lower. So if you have even less density, which means if you are more and more porous, what you can do? If you want to become more and more porous, what you can do? Tell me. Can you type? Kaijin? Yes, excellent. You add more and more hydrogen chloride. So that's why you can say you have more and more hydrogen chloride, more and more hydrogen chloride. So you're going to have more and more porous structures. Okay, effect of atmosphere of relative densities centered at 1000 degrees. Okay, so you can see the SCM picture is very, very different. Okay, so this is we explain what is coarsening. So obviously this one is coarsening, root 2. This one is densification 1. Okay. So keywords, ultimate goal. What is ultimate goal? Now I'm helping you to review. Okay, ultimate goal is trying to reach the relative density at a lower temperature. So obviously, you know, every time you have higher temperature, it is always have better densities. Okay, but the thing is, economically, we prefer to reach higher density at lower temperature. So this is ultimate goal. And two centerings. What are the two centerings? Can you type? What are two centerings? Solid and liquid. Solid and liquid. Okay, so there's two centering, that's solid and liquid. Okay, the driving force is what? Driving force is to reduce the total surface energy. Okay, reduce the total surface energy. That's the general force for sintering, right? Okay, then we have two roots. Root one is what? Root one is you have the densification first, followed by the grain growth later. That's root one, so which give you the densification. Root two is what? Root two is just become bigger. The grain become bigger and bigger and bigger and bigger. Okay, so that's coarsening, root two. Okay, so these are the keywords, few keywords so far. Okay, make sure you are very comfortable so that I can move on. Okay, because we just said if you want densification, you want root. Can everyone type? If you want densification, you want root what? Excellent, thank you. You root 1, 1, 1, 1, 1. I expect a lot of 1 here. Yeah, thank you, Sean. Thank you, thank you, all of you. Okay, I expect a lot of 1 here. Okay, if you want densification, you want root 1. But then, as a scientist, how can you make sure root 1 happen more? This is a very important concept. Okay, so then we have to learn all these fundamentals. Okay, so let's start with the first equation. Okay, so this equation we call is a Young's equation. So we don't talk about this radius case. We only talk about the sphere case. Okay, the sphere case with a radius, because you know almost all the particle is a sphere, right? The particle is a sphere. Okay, for sphere with radius r, it can be simplified as delta p equals to 2 gamma over r. So how can we get these equations? I give you an analogy. Okay, so maybe help you to understand. Okay, so this is a very good analogy to share with you. How can we derive this delta P? Okay, delta P. Okay, so you can imagine this balloon, right? This is a balloon. We just know. Okay, balloon, you become bigger and bigger and bigger. Okay, so there will be a pressure difference. Am I correct? So you have pressure difference in and outside. Obviously, in is larger or outside is larger. You have pressure inside and outside. Which side is bigger? This is P outside. Yeah, inside is bigger, right? Okay, thanks, JR. Okay, so inside is bigger. Okay, so this very large. So you will have a pressure difference. So this pressure difference, delta P is equals to P inside minus P outside. Okay, so this pressure difference, then you're going to have a force, correct? Right? You have. So this force, do you think is going to balance by what? Can you just roughly think? If for this a balloon case, roughly is going to, because there's a pressure difference, this pressure difference is going to be balanced by which one? Any force you have to have an equilibrium, right? Which one? Can someone tell me? Just from this balloon case. No, it's not pressure any, because pressure is here. Pressure, we talk about delta P. Delta P is pressure inside and outside. So you can see this balloon, right, become bigger and bigger and bigger. So which one make it not broken? You have this rubber, right? You see, outside you have a rubber. The rubber become bigger and bigger and bigger. Correct? Okay, so this is another concept. So which means what? Okay, so first of all, of course, this is a simple thing. I just want to help you to understand that. Okay, just use this way as an analogy for you to understand these equations. So the force induced by the pressure difference need to be balanced by the stretch of the rubber, right? But the stretch of rubber, the rubber is where? Rubber happen where? Tell me. Where's the rubber? Where's the balloon? Can you type the keywords here? Excellent. Very good. Surface. Exactly. Surface. Okay. So basically at the surface, at where? At the circumference of this. If we only talk about this, because at anywhere you need to have this mechanical equilibrium. So for example, if I cut this balloon in the middle, okay. So then this whole area, you need to have a mechanical equilibrium. So first of all, you have a pressure difference inside and outside is going to exert force on this plane. And this force is going to be equals to the stretch of the rubbers. Okay, so this is just more or less might help you to understand. Okay, so the force from the pressure difference equals to All these are you learn in your high school physics, but don't worry if you can't remember, doesn't matter, okay? So delta P times area. So delta P times area equals to force, right? Delta P times area of this one at this stage, because the radius is r, so will be 4 pi r squared. Pi r is the cross-section area, okay? Cross-section area, okay? Pi r squared. And also the force balance are balanced by the surface, the rubber, the stretch of the rubber. And as I said before, okay, remember these equations are, we said gamma times area equals to what? Gamma times area equals to what? Just now we calculate a lot already, right? Gamma times what? Times area equals to, yes, we spent a lot of time calculate this already. Okay, gamma times area equals to surface NH, okay? And also gamma times length is going to be equals to force. Okay, gamma times length is equals to force. Now I'm asking you, listen, okay? Now I'm asking you, so for this rubber, right? So where are the rubber? So what is this length now? So if I only talk about this shaded area, this one, give me a keywords here. So I already know because there's a gamma here. This is surface tension. You times what? You times the length. What is the length? Thank you so much, Yongjin. Thank you so much. It is the circumference. Okay. So the gamma times the circumference, because where's the rubber? The rubber only has a circumference. Okay. So it's going to be 2 pi r gamma. And these two have to balance with each other. And you quickly can come up these equations. Okay. Gamma equals to 2 gamma over r. Okay. This is definitely not required. It's not required. I am not requiring you anything. Just help you to understand, okay? Because I have some ways to help students to understand, okay? So I thought this may be a good way. So delta P equals to 2 gamma over R. 2 gamma over R. Okay, please be patient. Please be patient. I know when the math start to come in next week, there will be even more math, okay? So a lot of math there. It could be very complicated at the very beginning. As I said, after I teach you, you will definitely, all of you, 95% of all my students will understand it. So no worry. If all your seniors can understand, you will also. Okay. Let's continue. Okay. So this is a simple way, just help you to understand. Okay. There's another way which is more scientifically proven way. I mean, this is more often written in the textbook. Okay, there's another way to understand this one, which is delta mu. So delta mu, which is free energy per atoms. So what are these free energy per atoms? You can see, for example, right, this is particles, right? The particle have a lot of atoms inside, correct, right? This is particle. So particle have a lot of energy, particle have a lot of atoms inside, correct, right? So now let's calculate for one atoms. For one atoms, what is the free energy of this one atoms? Okay, so how can we calculate? How can we calculate? Okay, so the simple thing, we have used these tricks again a lot of time already, right? So first of all, you calculate the whole, right? You calculate the whole, then you divide by how many number? You see, we have used these tricks already, right? Okay, so first of all, we calculate how much is the free energy as a whole particles. So it's very simple, right? Because you have 4 pi r, because this is sphere, so 4 pi r squared times gamma. Okay, so this is a surface tension per unit area. We said before, gamma times area equals to NHR. Okay, gamma times area equals to NH. Okay, 4 pi r is the sphere's total surface area times gamma SV, right? In this case, gamma SV is going to be the total surface NH of this island or particles. Okay, then we divide in number. How can we calculate number? You have used this many times already, right? How can we calculate number? Remember last time we talked about molar volume divided by the number of each particles? So it's same here. Okay, if you know the total volume of this one, total volume of these particles, and also you know the atomic volume. So then I also know the atomic volume of each atoms. So I simply just use the total volume. So total volume of the spheres of the particles divided by the volume of one particles. This is atomic volume. This is atomic volume. Okay, atomic volume. Okay, so then you just do the differentiation. I trust you know all these things. Okay, in your math. So you do the differentiation. So this one will be something like this. This will be something like this. And then in the end, you will have a 2 so atomic volume, and also gamma, also R. So can you compare with this? So this one is delta P equals to 2 gamma over R. Yeah, my writing is so bad. Okay, so delta P equals to 2 gamma over R. So if you times and volume here, okay, volume here, atomic volume, which means 1 atomic volume, so we get the free energy per 1 atoms. Okay, free energy per 1 atoms is roughly the same, right? So which means delta mu is equals to delta P times atomic volume. Okay, so there's a very important concept here. Now I'm asking questions. Gamma is a constant, right? Is it gamma is a constant? Now I'm asking you, if the R become bigger, if the R become bigger, so the delta P is become smaller or bigger? Or the P, I mean, it's just like if, okay, the P is going to be inside, the pressure is going to be higher or lower? Inversely proportional, inversely proportional. So this is a very important concept, okay, which means your free energy per atoms or your pressure is actually inversely proportional to R. So that's why the particle size is so important, right? Why you need Bohr meaning? Tell me, why you need Bohr meaning? Can you type? Why you need Bohr meaning? Because you need reduce the particle size. Thank you, thank you. Yeah, we need reduce particle size. Particle size is very important. Okay, so this it is delta mu or delta P is actually inversely proportional to R. Now I'm asking you, so for one atoms, right, for example, I have one atoms which is inside the balloon, something like this. You have a lot of atoms here. And also you have some atoms on a flat surface. Flat surface. Okay, I think okay, ask this one. Okay, so now I'm asking you, which one is going to have higher energy? Maybe I ask a simple one first. Okay, for example, I have a big particle, also have a small particle. This is 1, this is 2. So which particle, the atoms inside that particle have higher free energy? Is 1 or 2? Higher free energy. I'm asking first question first. Which one? I see people answer 2. Any more 2? Excellent, excellent, excellent. Okay, okay. If I have 2 particles, I have 2 particles. This particle, this particle. Okay, so these 2 particles you have full of atoms. All of them have a lot of atoms inside, right? But we know for each of them, the free energy per 1 atoms is inversely proportional to R. Okay, so which means the atoms here, okay, is going to have lower free energy compared with the one of the smaller one here. Okay, okay, so it's inversely proportional. Why this is important? We're going to explain later. Okay, because this means when these 2 particles come together, so where the atoms go from 2 to 1 or 1 to 2. So let's say, because synchrony is what? Synchrony is particle come together, right? We said before you have particles, your particles, at the very beginning, you're in contact with vapor, but now you come together already, right? You come together. So now the atom will move. So the question is, where will the atom go? So the atom goes from 2 to 1 or 1 to 2. Can you answer this first? 2 to 1 or 1 to 2? Excellent. 2 to 1, right? Why is so? Why so? Yes, the atom is actually going from 2 to 1, right? Atom always going to higher energy or lower energy, tell me. So good, very good. Hey, your batch is very good, huh? Okay, yes, atom is going from higher energy to lower energy. Okay, so which means in centering, if these 2 guys are the contact with each other, so then these little small ones is going to surrender to the big ones, okay, join them as even bigger ones. Okay, so that is because the science behind it is simply because the free energy per 1 atoms is smaller in the bigger particles. Okay, So this one have higher energy per one atoms for the smaller particles. Okay, so that is the principle behind it. This is one question, okay. Second question, listen, okay. So you have particles here. Okay, one before is we have this one, right, small and big. Now if I have a sphere and also a flat one. So again, this is 1, this is 2. Now you tell me atom will move from where to where? Atom is going to move from 1 to 2 or 2 to 1? 1 to 2 or 2 to 1? Wow, you guys are really good. Okay, why is so? Because 2, what is R here? What is R for 2? What is R for 2? Infinity, excellent, right, correct, right? Because the R for the flat one is the is infinity, just like Earth, right? Why Earth looks like flat? Because the radius is so big. Okay, so it's the biggest possible radius already. Okay, so obviously, its atom actually is going to move from the sphere to the flat one. Sphere, okay, that's what we put here. Okay, at this moment, please don't get this one we call it a convex case. Convex, okay, convex. Don't worry about concave. I'm going to explain next week, okay? But don't worry at this moment. And because convex, R is larger than 0, then mu is larger than 0. So chemical potential of atom on such surface, which is larger than that one, the flat surface. Okay, so in this case, we call it a convex. I know you get confused, don't worry, okay? But just remember, we remember the easy simplest. Convex is more or less like a balloon case. Okay, so it's a convex case. It's the one you're familiar with. The radius is always positive. Okay, actually, there's another way we call it concave. The radius actually is negative. Okay, but we ignore the negative part first. Okay, don't worry. Okay, so we only talk about scenario 1. So this is scenario 1. Okay, which is you have 2 different size of particles. One is bigger, one is smaller. So you know which one is going to have a lower free energy, which one have higher. And also we have another case, which is you have one have radius, okay, we call it convex case, and also the other one is a flat one. But because it's a flat one, which means your R equals to infinity. R equals to infinity, okay? R equals to infinity, which means now your delta P equals to what? Delta P equals to what? Or delta mu or delta P equals to 0. Excellent, excellent. Okay, 0, which means because only when you have a shape, which means what? Only when you have a shape, when you have a radius, you will have a pressure difference. Correct, right? Pressure in and pressure outside. You will have pressure difference. Correct, right? When you have flat, the in and out is the same already. If a flat one is something like this. So inside, outside, they're equal, right? Because it's a flat one. Okay, so every time we talk about inside, outside, this is something like this. Okay, if it's flat one, yeah, delta P equals to surface tension. Okay, delta P equals to this one, 2 gamma over R. 2 gamma over R. Okay, so actually all things, well, I'm going to teach you a lot, but everything is about this R. Everything is about this R. Okay, everything is about this R. Okay, the radius. Okay, so let's continue. Okay, okay, we only have 10 more minutes. Okay, quickly ignore this. Only have this one. Okay, just these equations. So non-PC over P infinity. Okay, PC, which means okay, you have particles inside. You have PC, right? Or before we use PI, it doesn't matter inside or outside. Okay, outside is what? Outside is what? Outside is always what? Is what is the radius for outside? As I just said, it's a flat case, right? Outside is what? Outside is just a flat one, right? So it's an infinity, okay? Yeah, so that's why PC over P no or P infinity. Some people P no, doesn't matter. Different book use different names, okay? P, but anyways, outside is infinity. You don't have shape. Okay, so the key thing for this centering is about particle size. The particle size, okay, so every time if you have a shape, if you have like a spherical shape, you have a radius, then everything changes. The pressure is going to change. Okay, so this PC over P infinity is actually equals to 2 gamma. Again, you have this 2 gamma. gamma surface tension, right? And this is atomic volume, and this is Boltzmann constant, and this is R. Again, you have R here. You see, again you have R here, and you have a temperature. Now you add another one more thing, which is temperature. But doesn't matter. So this is just equations. And again, you can see non-PCA over P infinity is inversely proportional to R. So please remember the conclusion first. Conclusion is about the pressure inside. Our pressure, okay, is inversely proportional to R. Inversely proportional to R. Okay. So we can use this equation, have all sorts of like variations, a lot of variations, okay? And also please ignore all these variations, mass variations, okay? So you have also like a P, can you take out P naught? P naught is out, sorry. Also, as I said, some people use infinity or P naught, different book use different things, okay? Just don't confuse yourself. And exponential, if I put the exponential on both sides, exponential here, there's just a lot of variation there, no worry. Okay, you also have delta P over RT if you combine with this Young-Sabs equation now, okay? And also there's another one, P over P naught equals to 2 gamma B M R RT. This is a Boltzmann constant changed to gas constant, okay? So I just ignore the math because I'm not going to test you, okay? So just give you a very simple example here, okay? So calculate the vapor pressure of R, which is 90 nanometer water droplet at 20 degree. Assume that density of water is this, density is this, and R, which is gas constant, which is this, and the molar, this is molar weight, which is this. Okay, 1 mole, what is the weight here? Okay, so we simply just use the one equation we have derived here. As I said, it's not required. It's not required, okay, but I just want you to have the concept here, okay? So which means what? So again, this is water droplet, right? Water droplet. This water droplet is 90 nanometer. 90 nanometer. Okay, so inside you have a lot of atoms of the water atoms, a lot. Okay. So now let's calculate the pressure, vapor pressure. So we use that equation. The equation which is we have derived here. Okay, use this equation. We put exponential here. Okay, then put all this value in. So all this value looks very complicated. Actually, P naught is a constant because this one have no shape. You don't have shape, so the P naught is constant, and the gamma is constant. V is a constant, R is a constant, and T can be changed. Is it simple? Actually, everything else is constant. So you just put the value in. Okay, so it's not difficult. So it's only related to the R. Okay, so we just use all these equations, and from this equation we know we need to calculate the molar volume. So molar volume equals to what? Equals to molar weight divided by the density, right? That's volume. Weight divided by density equals to volume. So molar volume divided by density equals to molar weight. Okay. And then we put this one is a constant. This is surface tension, constant. This is molar volume, we just calculated. The R, which is radius, okay, radius, which is 19 nanometer. And the gas constant is constant. It's a constant. Gas constant must be constant, like gas constant, Boltzmann constant, all these are constant. And temperature, the temperature just need, remember, use Kelvin temperature, because 20 degree, use Kelvin temperature. So then, as we said, so then this one is going to be exponential, right? So which will be 0.0119. So which will be 0.0119. And also, as I said, P naught is also going to be a constant. This all can be found in the reference. And now we know if your particle water droplet is 90 nanometer, so the pressure actually inside is going to be equals to 17.745. 17.745, okay, 17.745. So outside is what? Outside is what? Can type? Outside is what? Outside is P what? P infinity or P naught? P naught. So outside is 17.535. So you can see, which means what? Which means once you become particle, you have a shape now. If you have a shape, then you have different pressure, or you can say you have a different free energy. Okay, so that's a very important concept, okay? So you have a tutorial question. Now I'm asking you, so if your water droplet is 900 now, much bigger, 10 times bigger. So what is this value? You give me a guess. Okay, give me a guess. So where this value, I just write the number here, okay? It's going to be 17.8 or 17.6. You choose. Now I change the R into 900. 900. 900. 17.6 or 17.8. Yeah, math answered 17.6. Any more answer? Which one you're going to choose? Which one are you going to choose? Excellent, excellent, 17.6. So you go back to calculate, okay? I leave this, can you just screen print? Because I think I leave it empty if I'm not wrong. Okay, so this is one of the tutorial question. Change from 990 to 900. Actually, the calculation is so simple already, right? But I don't teach you, I don't tell you. Okay, go back to calculate. Tell me the answer. Is it more close to 17.6 or 17.8? Okay. Okay. Second point. Second point. Important. Okay. So this, when R is larger than 0, this one more is like a balloon case. Balloon case. Okay. R is larger than 0 because delta P equals to 2 gamma over R. Okay, because R in this case is the one we are very familiar, right? Anytime balloon, right, you must have a radius, so it must be positive, right? So I is larger than delta mu is also larger than 0, delta P is also larger than 0. And R when it's infinity, R is actually equals to 0, right? As we said before, this is a fact one. This one is actually concave case, but we don't teach this one yet. We don't teach one this yet, okay? So later. But anyway, so you can imagine, as we just said before, so if you have atoms inside the radius which is larger, which is a convex case, this is convex, this is concave. I know it's very noisy, don't worry. As I said, after next week's tutorial and also the lessons, I'm sure 95% of you will understand, okay? But at this moment, can you simply just remember first? Okay, so the atoms is just like human being, okay? They prefer to go from the mountain to the land to the valley. Because I think before we already said, if you have a sphere and also you have a flat one, the atom is actually going from the sphere to the land. We have already just discussed, right? But remember here first, okay? Atom, just like human being. Yeah, we're just lazy, right? We want to lower our energy, right? Correct, right? It's easier, right? Correct, okay, so it's easier, much easier for you to go from the mountain, which is a convex, to the land. And the next week, we're further to talk about this R less than 0, which is concave, which is a valley. Okay, this is so important because without understanding this one, we cannot move further. Okay, so summary, ultimate goal. Yeah, only 1 more minute, okay. Ultimate goal, what is goal? Ultimate goal is to lower temperature, have higher density, right? Density, okay, 2 roots. Root 1 is what? Root 1 is densification followed by the green rows, right? Root 2 is what? Coarsening, become bigger and bigger, right? Okay, 2 centering, you have solid centering and the liquid centering, right? And also Yang-Sutter's equation, Kelvin equation, all these equations actually tell you the same thing. Well, the same thing, which is free energy, highest at convex, followed by the flat, followed by the concave. So why this is important is because the atom is going to move from the convex, then to the flat, to the concave. So we will spend a lot more time to expand this one next week. Okay, but at this moment, you just use yourself as an analogy to remember this. Okay, as a human being, you prefer to go from mountain to the land and to the valley. Okay, thank you. I stop recording. I will stay for a while and then